Hello everyone, my name is Edison Hong, and this is my second lab, Motion of a Falling Object. So, the agenda of this experiment is to introduce the purpose of it, the models through Newton's second law, gravitational force and drag force, computational models using tracker versus the glow script, and the conclusion on what this means and further questions. Now, what's the purpose of this lab? So the purpose of this lab is to observe and analyze motion of a falling object. In this case, I'm going to be using a crumpled up piece of paper, and I'm going to create computational models to simulate the object's motion under gravity and under combined effects of gravity and drag. So I'm going to be throwing it from a certain height down the y-axis in a straight line, and I'm going to be comparing it on tracker and glow script to evaluate the concept of terminal velocity. Now, let's get right into models. So, what kind of models or equations will we be using in this experiment? We'll be using Newton's second law to find the net force acting on an object by interactions with other objects. So, we can get the position update and velocity update formulas from Newton's second laws from deriving it, and we can use the gravitational force since our object is falling to the ground and is affected by gravity, and we'll be using the drag force, which is the opposed force to the gravitational force. And this is when the object interacts with the liquid air. Since our object falls somewhat slowly, there's drag. And there's an important note: if there's no drag, net force equals the force of gravity. So let's get into coding. So I'm going to be using this tracker model here. So my system right now is the paper ball, and I'm throwing it from certain height, and my surroundings are the earth and the air, and my initial conditions are the position, velocity, and time, and the position is at 0.0138 meters in the y direction, velocity is 0 meters per second all over, and the total time is 0.567 seconds. And I got it from the numbers that you can see here on the right. So, as you can see here, I plugged in the initial conditions, as I mentioned in the previous slide, and I have the proportionally constant set to 0. The net force will be the force of gravity. With the velocity update formula, I calculated the ball's final velocity in the positional update formula, as you can see with the formula code on the right, and yeah. So as you can see here, I ran the code from the last slide, and this is the graph of the gravity plus no drag. So as you can see here, there's a constant velocity, and it goes out a downward slope over time of the position. So as you can see here, this is the code for the gravitational plus drag force, and I have almost the same code as the two slides from before, but this time I factored in the drag constant force along with adding the drag force formula. And I have the combination of the drag force and gravitational force to give me the new net force for the gravitation and drag graph. So I ran the previous code that we had before for the gravitational and drag force, and here are the results. And I'll go into these graphs a little bit later on for further questions. So here are results. I put this in a Google Sheet with the tracker and the glow script numbers, and I observed that the computational model actually models the real world drag model. And some of the possible errors will be positioning center of the ball with the tracker, blurriness to some frames since I'm human, and it has some discrepancy there, the slight turn of the ball, and the ball is crumpled, so it's not smooth. So, what does this mean? And we'll be answering some further questions. So, what does this all mean? So, towards the end of the graphs, the velocity becomes constant. And there's zero net force because the force of gravity and drag are equal to each other. And the gravity and drag graph reach a terminal velocity faster. As you can see here on the bottom right, it does look like it's going at a much faster pace than the no drag graph. So, what if the ball was initially thrown downward? Would the terminal velocity be the same? So, the end velocity would still remain the same, and tossing it downward will cause it to slow down until it achieves the same velocity. And terminal velocity is reached more quickly compared to if the ball was dropped from rest. So, our last question is, what models predict the terminal velocity? Force of gravity pointing down is the same as the force of gravity pointing up. As you can see, this guy here, and it experiences no net force at terminal velocity, and the drag is important to the terminal velocity here. So, to wrap it up, we used Newton's second law, the gravitational force, and the drag force to model the motion of the paper ball, and we recorded and analyzed the vertical motion of a paper ball in the tracker and then compared the data to the glow script in the computational model. And we know that drag is present with gravity. Thank you very much.